Good afternoon everyone. Welcome back in my channel Dr.Satendra. Dear friends, if you want this type of videos relative to mathematics for higher level, then you need to subscribe, share and like my videos and my channel. Today we will discuss CR equation, that is Cauchy-Riemann equation in polar form and its derivative form. Now to discuss Cauchy-Riemann equation in polar form. Cauchy-Riemann equations in polar form. Has been come in AKTU 2016. Now derivation of Cauchy-Riemann equation in polar form. Let W equal Fz is an analytic function. Since Z equal R e to the power I theta is a point in polar form. Now W equal to U plus IV, this is equal to F R e to the power I theta. This is equation number A. Now differentiate above equation with respect to R partially. Now partially differential with respect to partial differential above equation with respect to R, that is del U del R plus I del V del R. This is equal to F dash R e to the power I theta into e to the power I theta. This is equation number first. Similarly, partial differentiation with respect to theta in equation number A, that is del U upon del theta plus I del V upon del theta equal to F dash R e to the power I theta into I R e to the power I theta. Now we can write I R common, F dash R e to the power I theta into e to the power I theta. The value of F dash R e to the power I theta into e to the power I theta from equation number first. Then we get IR del U del R plus I del V upon del R. This is equal to del U upon del theta plus I del V upon del theta. Now comparing real and imaginary parts. The real part of this and this is equal to imaginary part of this. Now del U upon del R, this is the imaginary part. Now 1 upon R del V upon del theta. One equation. We get imaginary part. Now real part del U upon del theta. This is the real part. Now real part is this minus r del v upon del r. These are the CR equation in polar form. CR equation in polar form. Now, derivation of derivative. Derivation of derivative of w equal to fz. Derivative of w equal to fz. Answer. Let w is equal to fz be an analytic function, be an analytic function. Now differentiate dw upon dz equal to f dash z. This equivalent to del u upon del x plus I del v upon del x. Now we can say del upon del x common, u plus iv. This is equal to del w upon del x. Since w equal to u plus iv, that is del w upon del x. Now we can write del w upon del x. This is equivalent to now dw upon dz, del w upon del x, del w upon del r upon del x, plus del w upon del theta upon del x. Now we want to show that the position of derivative of function in polar form. Now del w upon del x convert into del w upon del r upon del x plus del w upon del theta upon del x. Now for polar form, x equal to r cos theta, y equal to r sin theta. Now squaring both, x square plus y square equal to r square, and divide, then we get theta equal to tan inverse y upon x. Now differentiate partially with respect to x to r, del r upon del x equal to 2x, that is del r upon del x equal to x upon r. The value of x, r cos theta upon r cancel by this. Now del r upon del x is equal to cos theta. Similarly, we can write for del theta upon del x, partial differential with respect to x, del theta upon del x, the differential of tan inverse y upon x equal to 1 upon 1 plus y square upon x square, or into minus y upon x square. Now we get minus y upon x square plus y square. The value of minus y r sin theta upon x square plus y square equal to r square. Now del theta upon del x equal minus sin theta upon r. This is the value of del theta upon del x. So dw upon dz equal, now we put del r upon del x cos theta and del theta upon del x minus sin theta upon r in this. Now if we want, there are two methods to solve of derivative of fz, now in terms of r or in terms of theta. First we want to show dw upon dz in terms of r. Now we put the value of del w upon del theta as follows. Value of del r upon del x cos theta Now del W upon del R as it. Del W upon del theta, del upon del theta u plus iv. We put W u plus iv. Now del theta upon del x minus sin theta upon r. Since we want to the derivative of function in forms of del W upon del r. Now we break del W upon del theta as. Now second term part we want to del W upon del z in terms of del W upon del theta. When we break del r upon del W upon del r in next part. Now cos theta del W upon del r as it plus del u upon del theta plus I del v upon del theta minus sin theta upon r. Now using CR equation in polar form, the value of del u upon del theta minus r del v upon del r in this, and the value of del v upon del theta 1 upon r into del u upon del r in this. Then we get cos theta del W upon del r as it plus value of del u upon del theta minus r del v upon del r plus I del v upon del theta r del u upon del r minus sin theta upon r as it. Now we take common I upon r. I r. तो cos theta del W upon del r as it plus I r common del u upon del r plus I del v upon del r minus sin theta upon r as it. R cancel by this. Therefore dw upon dz equal cos theta del W upon del r minus sin I sin theta. Now we take del upon del r common, u plus iv. This is the value of W. Now cos theta del W upon del r minus I sin theta del W upon del r. Now we can common del W upon del r, so cos theta minus I sin theta del W upon del r. Now derivative form of W is equal to fz e to the power minus I theta del W upon del r. This is the derivative form of analytic function W upon W equal to fz. Now another form. Now another form of derivative. Since dw upon dz equal to del W upon del r upon del x plus del W upon del theta upon del x can be written as in above. Now we can calculate del r upon del x, del theta upon del x. So we to show derivative of function in terms of del W upon del theta. Now break del W upon del r and putting the value del r upon del x and del theta upon del x. The value of del r upon del x cos theta. Now break del W upon del r. The value of W u plus iv. My del W upon del theta value sin theta upon r negative. Now del W upon del theta as it. Cos theta del u del r plus I del V del R minus sin theta upon R del W upon del theta as it. Now the value of del W del U upon del R by polar form cos theta, value of del U upon del R 1 upon R del V upon del theta plus I, the value of del V del R minus 1 upon R del U del theta. Now minus sin theta upon R del W upon del theta as it. Now taking the common, minus I upon R minus I upon R common, cos theta del U del theta plus I del V del theta minus sin theta upon R del W upon del theta as it, minus I upon R cos theta, this is the value of del upon del theta U plus IV, minus sin theta upon R del W upon del theta minus I upon R cos theta del W upon del theta minus sin theta upon R. This is the value of W del W upon del theta as it. Now common del W upon del theta, so minus I upon R common, cos theta minus I sin theta del W upon del theta minus I upon R e to the power minus I theta del W upon del theta, the value of dW upon dz, that is another form of derivative. This is the complete of the topic. Now second topic, harmonic function. What is harmonic function? Harmonic a function of xy variable, a function of x comma y variable satisfies Laplace equation is known as harmonic function. Now again repeat, a function of x comma y variable satisfy Laplace equation is known as harmonic function. Now theorem. Statement: if W is equal to, or say Fz equal to U plus IV, is an analytic function then U and V are both harmonic function. Now repeat the statement. W is equal to Fz is an analytic function. Now the part of Fz that is u and v. U is the real part, v is the imaginary part of analytic function. Both are harmonic. Now prove. Since fz equal u plus iv is an analytic function, then u and v satisfy CR equation. Cauchy-Riemann equation. Now CR equation is del u upon del x equal to del v upon del y, equation number first, and del u upon del y equal minus del v upon del x. This is the CR equation in Cartesian form. Now partial differentiation with respect to x in equation first. Del 2u del x2 equal to del 2v del x del y. Similarly, partial differentiation with respect to y in equation number 2. Del 2u del y2 is equal to minus del 2v del y del x. This is equal to minus del 2v upon del x del y. Now putting the value of del 2v upon del x del y, this is equal to del 2u del x2 in this. Now del 2u del y2 equal minus del 2u del x2, implies del 2u del x2 plus del 2u del y2 will be 0. Therefore, function u satisfies Laplace equation. This is Laplace equation. Laplace equation of u, that is u is harmonic. U is harmonic. U is harmonic function. Now for second, now we want to show that v will be harmonic. For this, partial differentiation with respect to y in equation number first. So del 2v del y2 equal to del 2u del y del x. Similarly, partial differentiation with respect to x in equation number 2. That is del 2v del x2 minus del 2u del x del y. This can be written as minus del 2u del y del x. The value of del 2u upon del x2 put here, del 2v upon del y2, that is del 2v del x2 equal to minus del 2v del y2. Now this del 2v upon del x2 plus del 2v upon del y2 is equal to 0. This is a Laplace equation in v, imply v is harmonic. Harmonic function. Now next question is, every analytic function every analytic function fz equal to u plus iv, that w is equal to fz. Define two families of curve. Define two family of curves uxy equal c1 and vxy equal c2, which form an orthogonal system. Which form an orthogonal system. Proof. W is equal to fz is an analytic function have two family of curve uxy equal to c1 and vxy is equal to c2. Family of curves uxy equal to c1, equation number first, or vxy equation number c2. Vxy equal to c2, equation number 2. Now differentiate in equation number first. Del u upon del x dx upon dx plus del u del y dy upon dx equal to 0. Now dy upon dx say m1 equal to minus del u upon del x upon del u upon del y, equation number 3. This is the slope of first family of curve. Differentiate in equation number 2, we get del v upon del x from equation number 2, del v upon del x dx upon dx plus del v upon del y dy upon dx equal to 0. Now dy upon dx say m2, that is slope of second family of curves, equation number 4. Now equation 3 multiplied by equation 4, that is m1 into m2. Now we can say this is the slope of both curves minus del u upon del x upon del u upon del y into minus del v upon del x upon del v upon del y. But this is the part of analytic function. Now it satisfies CR equation, where CR equation del u upon del x is equal to del v del y, or del u upon del y equal to minus del v upon del x. Now minus del u upon del x as it, del u del y as it. Now del v upon del x is equal to del u upon del y by CR equation, or the value of del v upon del y, del u upon del x. Now this is cancelled by this, or this cancelled by this. This is equal to minus 1. m1 into m2 is equal to minus 1. Hence both family of curves intersect at right angle that is they form an orthogonal form, that is they form an orthogonal form.